What's going on, everybody, and welcome to part 5 of the reinforcement machine learning series. In this video and subsequent videos, we're going to be talking about deep Q learning, or DQNs, or deep Q networks. And to start, the prerequisites: if you don't know deep learning, stop, pump the brakes. You got to learn deep learning. So if you want, you can go to the homepage of pythonprogramming.net, click on the machine learning here, and then do this deep learning basics with Python, TensorFlow, and Keras. At least do like the first two tutorials, I want to say. Yeah, getting it, loading in your own data, probably the first 3, especially since we're using ConfNets. Do the first 3, and then come back to this, because otherwise you're going to be so lost. So, okay, deep Q learning. Basically, it got its start with the following paper, this human level control through deep reinforcement learning. If you've ever looked up reinforcement learning, first you found that all the tutorials suck, and hopefully not this one. And then you've seen the following image. So this is how the deep query network, or deep Q network, is going to learn. So what's going to happen is you've got this input. In this case, it's an image. You've got some convolution layers. They don't have to be convolution layers. Some fully connected layers. You don't have to have those. But you've got some sort of deep neural network. And then you've got your output layer. And your output layer is going to map directly to various actions that you could take. And it's going to do so with a linear output. So it's a regression model with many outputs, not just one. Now, some people did try to do just one output per, so basically to have a model per possible action. But it doesn't really work well, and that's super, that's gonna take a really long time to train. So anyways, here's another example. It's beautiful, really beautiful. You got input values. So again, it doesn't have to be an image. You know, this could be delta X, delta Y for the food, delta X, delta Y for the enemy, for example. That could be your input. Boom. Then you've got your hidden layers. Again, they could be convolution, they could be dense, they could be recurrent, whatever you want there. And then here you've got your output, again, with a linear activation. So it's just going to output these scalar values. Well, these are your Q values. They map directly to the various actions you could take. So in this case, let's say this was your output. You would take the argmax. Well, the argmax, or the max value here, is 9.5, and the values are, you know, or basically if we were to map this and get the index values, it would be 0, 1, 2, 3. So argmax would be 1. So whatever action 1 is, that would be the move that we would make. Okay, so we've replaced this Q table with a deep neural network. The benefit here is we can learn way more complex environments. First of all, we can learn more complex environments just because a deep neural network is capable of actually mapping that. Also, a deep neural network can take actions that it's never seen before. So with Q learning, if a certain scenario presented itself and it was outside of any of the discrete combinations that we've ever seen, well, it's going to take a random action because it got initialized randomly. A deep neural network, on the other hand, is not. It can actually recognize things that are similar, but it's never seen this thing before, and it can act accordingly. So first of all, a deep neural network is going to do better in that case. So in that way, it can solve for way more complex environments. But also, as we saw, as you just even barely increase that discrete size of your Q table, the amount of memory that's required to maintain that Q table just explodes, right? And it both in terms of your observation space size, or your discrete observation space size, but also in your actions. So in our case, up to this point, we've only taken 4. I'd like to introduce a few more actions moving forward. You know, so what we're going to do is we're going to keep the diagonal moves, but also allow for just straight cardinal, like up, down, left, right. As well as don't move. So we're going to introduce all of those as well. Anyway, so for those 2 reasons, neural networks are way better. The downside is neural networks are kind of finicky. So we're going to have to handle for a lot of things that are finicky about neural networks. Also, it's going to take a lot longer to train. So on an identical model, or an identical environment, like in the blob-env, where it took our Q table minutes to fully populate, basically. It's just a brute force operation, basically. So if it's small enough, you know, your CPU can handle it. Where it took minutes for a Q table, it's going to take hours for Q learning. But the benefit is where it takes, it's going to take hours for deep Q learning. But the benefit here is for certain environments where it takes, yes, a long time, like weeks for deep Q learning to learn an environment, it would require, petabytes of memory for a Q table to figure it out. Okay. So there's your difference. So really they're going to solve different types of environments, and honestly Q learning is pretty much useless. You can use it for cool, novel, little niche things for sure, but you're not going to find too much use for it in the real world, I don't think, whereas deep Q learning, you can actually start to apply it to really cool things. So anyways, enough jibber jabber. The last concept I want to do before we get into actually writing code is right here, this learned value change. So before, the new Q function basically was this whole thing, whereas the neural network kind of solves for this, like the learning rate and all that, and just updating values. This is solved through backpropagation and fancy things. But we still want to retain the future values because neural networks don't care. They don't give a heck about future. They care about right now. What is this thing? What is this exact value? They don't care about, well, what does this chain of events do? Other than a recurrent neural network, I suppose, but really a recurrent neural network cares about the history, not the future. So anyways, in this case, we still want to retain this, so we are still going to use this. And basically the way we're going to do this is every step this agent takes, we still need to update that Q value. So what we're going to do is we query for the Q value, we take that action, or a random one, depending on epsilon. Then we resample the environment, figure out what what the next reward would be, and then we can calculate this new Q value, and then do a fit operation. So people who are familiar with deep neural networks are already like, wow, that's a lot of fits. Yep, sure is. Also, that's one fit at a time. So as you're going to see when we go to write this code, we actually have to handle for that as well, because that would make for a very unstable neural network. So there's two ways that we're handling for that. But with that, I think we're just going to jump in the code, because I think it'll make more sense you just coding it and covering it as we get to those points. Okay, so hopefully that was enough information. Like I said, all the tutorials I've ever seen on deep Q learning have been terrible, and there's like so much information that's left out that, to get the overarching concept, honestly, this picture is enough. But then when it comes time to actually look at code and how it really will work, like, can you sit down and code it after you read someone's tutorial? My hope is you really can after this one, but otherwise I don't think a tutorial exists for doing it. So anyways, let's get started. So the first thing we're going to do is I'm going to we're going to at least hopefully code our agent, at least the model, and talk about some of the parameters, and then probably in the next tutorial we'll do fitment or training basically and all that. So anyway, class DQN agent, and this agent, let's just do define create model first. This should be fairly basic. It's just going to be a convnet. We don't have to do a convnet. I'm just going to do one just so you can more easily translate this to something else. So the first thing you should do anytime you learn something is go try to apply it to something else. So try it, and then you'll immediately, because it might make sense to you as you're listening to me talk about it, but then you go to try to apply it, and then suddenly it doesn't work, or you're confused, or you realize, oh, I don't really actually know how to do this. So anyway, the first thing you should do, try to apply it. Someone complained recently about my drinking on camera, saying they don't want to hear me gulp. I'm drinking because my mouth is dry, and the most annoying thing ever is listening to someone talk with a dry mouth. So you're welcome, jerk. So anyway, create model. Okay, so we'll start with model equals a sequential model, and now let's go ahead and make some imports. So the first thing that I need to bring in is from keras.models. Let's import sequential, and then we're going to say from keras.layers, let's import dense dropout conv 2D max pool 2D activation flatten. I think that's everything. Sorry, that ran over my face. My bad. Anyway, there we go. Dense dropout conv duty. Max pool 2D. And actually that's max pooling 2D. Activation and flatten. Okay, those are all of the imports. Also, you can always go to the text-based version of tutorials. If code runs over my ugly mug, you can check those out. Oh, actually, I don't even know. Maybe at the very end it'll be there. Anyway, by the time you need it, it'll be there. Anyways, okay, so we got that stuff. The other thing I'll go ahead and import to is from keros.callback. So let's import tensor board. We need other things, but I want to cover them when we get there. So model is equal to a sequential model. Then we're going to say model.add, and then we're going to start adding conv to capital D. Let me fix that as well. Cool. Conv 2D, which will give us 256 convolutions, and the convolution window will be a 3x3, and then input underscore shape, and this is going to be equal to it will say env dot observation space values. Shape observation space values, and then close this off. And this doesn't quite yet exist. We have to create the environment. I'm still a little uncertain if I'm going to actually rewrite the environment, because it's converted to object-oriented programming now. I may not actually, like, we might just copy and paste the updated environment, and I'll just talk about it, because otherwise it'll take like an hour to to go over that. So anyways, but this will exist at some point in the near future. Then once we've done that, I guess let me zoom out a little bit since we're running out of space here. The next thing that we're going to do is we'll say model.add. So that's our conv layer. We're going to add an activation, and the activation here we'll use rectified linear. And then model.add max pooling 2D, and we'll use a 2x2 window. And again, if you don't know what max pooling is or convolutions, check out that basics tutorial because I cover it. And I also have beautifully drawn photos. If you really like my other photo, you'll love those photos. Then after the max pooling, we're going to say model.add, and we're going to add a dropout layer, and we'll drop out 20%. And then we're just going to do the same thing again. So this will be 2x256. So copy pasta. We don't need to include the environment shape again, or the input shape rather. So I'll do this. 1, 2, 3. Okay. So 2x256. Then we're going to say model.add. We're going to do a flatten here so we can pass it through dense layers. And then we'll say model.add. We'll throw in a dense 64 layer. And then finally, model.add a dense layer, and it'll be env.action space size, and then the activation will be linear, and then model.compile, and we'll say loss is MSE for mean squared error. Optimizer will be the Atom optimizer with a learning rate of 0.001. And then metrics, we will track accuracy. Okay, so that is our model. Again, sample code is in, there will be a link in the description to the sample code, so if you've missed anything, you can check that out. Okay, so, and then Atom, we don't actually have Atom imported, so let's go ahead and grab that as well. So from keros.optimizers, import Atom. Just for the record too, if anybody's watching this in the future, this is still TensorFlow like 1.15. I don't really know actually. I don't know what version I'm on, but it's not TensorFlow 2 yet. So keep that in mind. So some things might change by then, and if it has changed, check the comments. And then when it finally actually does truly matter what version of TensorFlow I'm on, I will let you guys know. It's also kind of expected that you guys will know how to install TensorFlow and Keras. I'm not going to cover that. Again, for that, go to the basics tutorial. So anyway, model compile. Okay, then we will return that model. Okay, so that's our model. Then define init self. And then now we're going to do the init method for this model. So we're going to say self.model equals create underscore model. And then, so that is going, what is your problem? Why are you unhappy? What the heck am I missing? Oh, self.create model. More coffee is definitely necessary. Okay, self.model is create model. So that's going to be our main model. But then we need what's going to be called our target model. What the heck, Syntax? Let's write that first. So we'll call this target model equals self.create model. But then we're going to say self.target model dot set underscore weights, and we want to set the weights to be exactly the same as self.model.get underscore weights. Okay, so what's going on here? So we are going to wind up having two models here, and the reason why we want to do that is kind of there's a few reasons, but mostly it's because this model is going to be going crazy. So first of all, the model itself is initialized randomly, as all neural networks are. But we also are going to initialize with an epsilon likely of 1. So the agent is also going to be taking random actions, meaningless. So initially, this model is going to be trying to fit to a whole bunch of random. And that's going to be useless. But eventually, as it's explored, as it's gotten rewards, it's going to start to hopefully figure something out. But the problem is we're doing a dot predict for every single step this agent takes. And what we want to have is some sort of consistency in those dot predicts that we're doing. Because besides doing a dot predict every single step, we're also doing a dot fit every single step. So this model, especially initially, is just going to be like all over the place as it's attempting to figure things out randomly. So the way we're going to compensate for that is we're going to have two models. So we've got self.model. This is the model that we're dot fitting every step. And then we have self.target model. This model, this is the one that we're doing a dot predict every step. And I would even say this is what we dot predict against every step, and then this is the one that gets trained every step. Make note of that because you'll probably forget. So then what happens is after some number of steps or episodes or whatever, you'll re-update your target model. So you'll just set the weights to be equal to model again. So this just keeps a little bit of sanity in your predictions, right? So in the predictions that you're making, this is how you'll have a little bit of stability and consistency so your model can actually learn something, because it's just going to be, there's so much randomness, it's going to be very challenging initially. And so long as you're doing things randomly. Okay, so that's one way we are handling for the chaos that is about to ensue. Next, we're going to have self.replay underscore memory, and that is going to be a DQ or DQ. I always forget how to pronounce that. To use that, we're going to say from collections import DQ. And if you don't know what a DQ is, it is a set length. Think of it as like an array or a list that you can say, I want this list to be max size. So we're going to say max len equals replay memory size. And And let's go ahead and just set that real quick. We'll just say boom, and we'll set this to 50,000. Also, a cool little trick I recently learned was you can use underscores in place of commas. So Python sees this as 50,000, but it's a little more human readable. Like this number is a little harder, but then especially like once you have like a number like this, the underscore suddenly becomes very useful. So cool. So don't do a plus though. Underscore. Cool. So that's our replay memory size. So what the heck is this? So the replay memory, so we talked about how we keep the predictions, so how we keep the agent taking consistent-ish. So at least the agent is taking steps consistent with the model over time, okay? I'm trying to think of a great way to word that, but so we've got the prediction consistency sort of under control. It's still going to be crazy at the start, period. But this is that we've got that settled. Now we need to handle for the fitment craziness that is going to ensue, because we have, you know, we've got two models, so we've slowed down one way of working with that model, but the other one's still going to be crazy. So self.model is still going to be .fit every single step, but not only is it getting a .fit every single step, it's getting a .fit of one value every single step. So again, assuming you're not new to neural networks, you know that we train neural networks with a batch. And part of the reason why we do that is, one, it's quicker, but it also tends to have better results. Not necessarily the higher the batch you use. At some point, the batch size gets too big. But to have some sort of batch size used, it generally will result in a more stable model and just learning over time. So if you just fit with one thing, it's going to adjust all those weights in accordance to that one thing, and then it's going to get to the new thing, do another fit, and then it's going to adjust all the weights in accordance to that one thing, as opposed to if you throw in a batch of 64 things, it's going to adjust all the weights in accordance to all 64 things. So it's not going to overfit to one sample and then go to the next sample and overfit to that sample and then go to another, you know what I'm saying? So so we want to handle for that too, and the way that we do that is we have this replay memory. So we take this replay memory, and that can be, let's say, 50,000 steps, okay? And then we take a random sampling of those 50,000 steps, and that's the batch that we're going to feed off of, so train the neural network off of. So that's how we're getting stability in both the training network that's getting updated every single step, but hopefully we're smoothing that out a little bit. And then we're smoothing out the predictions because we're also not allowing the prediction model to be updated every step. Instead, it's being updated, let's say, every 5 episodes or whatever we intend to go with. These are all hyperparameters or really constants that we're going to set at the top of our program. Okay, replay memory. Okay, so the next thing is going to be self.tensor tensor board, and that's going to be equal to modified tensor board, and we're going to set log underscore dir to be logs slash var dash var, and we're going to make this an f string, and we're going to import time. If you're want to say 3.5 or younger Python, you can't do f strings. You'll have to do a dot format or whatever. And so for the logs, we're going to say model underscore name, and then we're going to say int time.time. This is just so we can kind of keep track of what's what. And then the next thing I want to do, I thought it was getting pissy at me for this. Anyway, let's go ahead and set model name before I forget. And for now, just it's whatever you want. I'm going to say a 256 by 2, because later you might try a 32 by 2 and a 64 by 2. And anyways, and by 256 by 2, I mean the neural network. It's a 256 by 2 convnet. So we've got tensor board done. Obviously, this doesn't yet exist. I'll talk about that in a moment. And then finally, self.target update counter equals 0. So we're going to use this to track internally when we are ready to update that target model. So this, this thing here that we've explained why we want to do that. So the next thing we want is, I I'm not going to write out that. So go to the text-based version of the tutorial, and we're going to grab this updated this updated TensorBoard class. Did we already pull? I think we already pulled in TensorBoard, but what I really want is this right here, this whole class. I'm gonna, oops, I want that comment too. I'm gonna copy that. I don't really see any benefit for us writing that, but I'll explain why we want that here in a moment. Paste that in, cool. So what this is doing is it's just modifying the TensorBoard functionality from TensorFlow and Keras. So by default, Keras wants to update this TensorBoard file, this log file, every time we do a .fit. Well, we're doing a .fit, about 200 times an episode. And then we're going to do like 25,000 episodes. So first of all, I'm sorry, I think I used the word update log file. It wants to create a new log file per .fit. Well, we don't want that. We want just one log file. So having this is going to solve quite a few things. This was written by Daniel. And basically, one, the I/O was taking a lot of time. So just simply writing the new file was sometimes taking longer than a .fit. But also, we've got all these extra files. Each one was 200 kilobytes. Not necessary. And yeah, so just a bunch of, it was just not constructive to do this. I guess that's the behavior because most neural networks are just going to fit once on some sort of cycle and it's not a big deal. But for deep Q learning where you're fitting just constantly, something needed to be done. Okay. So that is our modified TensorBoard. Now what we're going to do is go back to our DQN agent. So that's our init method. Let me just kind of clean this up a little bit. I want these kind of separated out. I don't want that separated out. I don't know. I can't really decide what I want. So I'll just leave that. So then create model. Let's go ahead. Let me see if I can hopefully, well, we're not going to finish this, but let's add in one more method. So we're going to say define, and in this one, we're going to say update underscore replay underscore memory, self, and then transition. Can we type? So then we're going to say self dot replay underscore memory dot append wow, I really want to call that transition. So transition is just going to be your observation space, action, reward, new observation space, and then whether or not it was done. So we need to do that so we can do that new Q formula. So that's all we're doing there. Hopefully that'll probably make more sense when we actually get to actually use self.update replay memory or agent.update replay memory. Finally, yeah, we'll do this one last method and then we'll save train for the next tutorial. So that's going to take a while. So define get queues. So we will get queues self terminal state and then step. And then, so this will be return a self.model underscore predict. And we're going to say the NumPy array. I don't think we've imported NumPy. We'll grab that soon. Of the state dot reshape -1. And then we're going to say asterisk state dot shape. All that's doing is unpacking state. And, oh, did I? I sure did. Terminal state. That's for train. Right now we're just passing state here. So np array state.shape and then we're going to do div by 255 and then 0. So model.predict always returns a list. Even though in this case we're really only predicting against one element, it's still going to be a list of one element or an array of one element. So we still want the 0th element there. Div by 255 is because we're passing in this RGB image data, so you can very easily normalize that data by just simply dividing by 255. Okay, so that's it. Let's go ahead and go up to the very top here. Let me import NumPy as NP. So let's say import NumPy as NP. Let me go ahead and save that. And I think I'm going to save train for the next tutorial because that's going to take a while. So quick shout out to the recent, well, not recent actually, these are my long-term channel members, people who have been sticking around for a while. Reginald Roberts, 7 months. Luis Fernando, 7 months. Stefan R. Scoot Harwood, 8 months. Amperhammer, 8 months. Edward William Sams, 9 months. And Abhijit, 10 months. That's quite a while, you guys. Thank you guys all for your support. And if you guys have any questions, comments, concerns, whatever, feel free to leave them below. If anything up to this point is confusing or you want to get a little more information, again, comments below, or come join us in discord.gg/Syntax. If you think I've done something wrong or said something wrong, I'm sure I have. Feel free to let me know. And yeah, I'm hoping that you guys can get through this tutorial series here and actually be able to use this stuff. I think right now, like I said, I could not find a tutorial or any information to actually do this kind of stuff that actually made sense or actually explained everything. So just a lot of copying and pasting going on. So my hope is that you guys can actually get through this and know how to do this yourself. So that's my goal. So if you're having trouble getting to that point, let me know, because I need to fix that. So anyways, I will see you guys in the next video where we will do the train method, and then we might only do the train method, but hopefully we can do the environment. I'm thinking I might just copy the environment. We made some tweaks to the environment, and we made that object oriented. And so I might just like copy that, because the environment honestly has not changed. We just made it object oriented just to make it easier. You know, there's like little tweaks made, and I think I'm just going to talk about the tweaks that were made, and that be it. That way, hopefully, maybe in the next tutorial, we can actually do the train method here, talk about that deep Q learning stuff, and hopefully get a model training by the next video. So I'll think about that. You can leave your opinion below, but probably by the time you've seen this, I will have already made my decision. So anyway, yeah, till next time, everybody.